So we were talking about the pitching moment of the wing, and we defined some geometries of different points on the wing last time, and then we derived this equation for the total moment. There's the pure couple. And then we had the components of the lift and the drag times their various moment arms. And we get the sine and cosine because the lift and the weight, the lift and the drag act perpendicular and parallel to V infinity, not to the moment arms. That's the moment arm for that. And there was the vertical moment arm, ZW. And so this is a big complicated equation. We'd like to simplify it if we can. So for some cases, we can say that the angle of attack is small, like if we're doing a cruise flight condition, not near stall, because if we're near stall, the angle of attack is pretty high. If we have a small angle of attack, then we can make some approximations here. We can change the cosine as approximately 1 here. The sine can be approximated by the angle itself in radians. Hopefully we've done a good job designing the aerodynamics and we get a much larger lift than the drag. And most airplanes are designed where that vertical dimension, the Z up to the CG, is pretty small, right? Because usually the CG is in line with the center line of the airplane. And so we could say that this is much less than these kind of dimensions here. So that allows us to start knocking some of these terms out. Let's see here. This sine is going to be the angle of attack here. And the cosine, again, is going to be 1. Then we start looking at small stuff and big stuff. And we look here and we notice that both of these are small. And we know if we take a small number and multiply it by another small number, it gets smaller, right? Like 0.1 times 0.1 becomes 0.001. And so this small product tends to be smaller than the lift here because the drag is small and the angle of attack is small. And the same thing on here. Here we've got a small number times what we said is a pretty small number. And same deal here. The drag we said was small, lift. So really we're going to say, well, this term right here is much bigger than anything else for small angles of attack. So these kind of cases, this is all we have left. Like that. So we've simplified it a lot. And then in aerodynamics, we like to deal with like lift coefficient, drag coefficient, pitching moment coefficient. So we divide by Q infinity S C bar to non-dimensionalize. And that's, we just define the coefficients in terms of these things. And so now you can see, well, why we made these H's non-dimensional with respect to C bar is because we're going to divide by C bar here. And so we're just left with the H's. We could have made them distances X's, and then when we divided by C bar, then they would have turned into the H's at that point anyway. And so this is called the pitching moment coefficient of the wing. This is the pitching moment coefficient of the pure couple of the aircraft. And then lift divided by Q infinity. Yes, that's the lift coefficient. So now this equation is entirely in terms of coefficients. So what we have is Cm we put the W because this is the wing and we're going to add a tail here in a minute. So I'll erase some of this. There we go. So this is for the wing. Now there's more to the airplane than the wing. There's the tail, so we have to do the tail next. There's also a fuselage or a body. And that's pretty complicated to figure out. Usually the effect of the fuselage on the pitching moment is pretty small. And so we just lump it all together and say, okay, well, put the wing and the body together, and we'll call it wing body. Now that sounds like you're going, well, that's kind of a kludge. Yeah, it is. We're saying, well, this equation represents the wing and the fuselage put together. And we'd need some extra formulas to estimate the change between just the wing alone and the wing with the fuselage. Typically done by some charts or doing a test in the wind tunnel to figure out what the difference is. And then how do we calculate the lift of the wing? Well, we have our lift curve slope of the wing or the wing body together. We multiply by the angle of attack. Again, why can we do that? Why is there no intercept here? It's because we defined this angle relative to the zero lift line. Remember that we said there's a line through the wing where if you're at this angle, you get zero lift. So we're just defining our measure of angle relative to where we get zero lift. There's no reason why you have to do that. We could change the lift curve axes. That's really all you're doing. If you have an axis here, you either say, okay, well, my curve looks like this, or to that point, and that's how I measure alpha, is from that origin rather than some other origin. So for the purposes of this class, we're going to, well, for the wing, we put the origin where the lift is zero, so we can calculate the lift like that. Okay, we need to do the tail. So there's the wing. We're going to add the tail to it. So everybody caught up here? I'm going to shift the projector over to the other, or the camera over to the other screen. You guys good? You guys can see this. Unfortunately, I can't show it to them as well. I'd like to be able to go back and forth, and that way you can catch up, but it's the way it is. All right, so now we need the tail. So we're going to do the pitching moment of the tail. We're going to draw the zero lift line that we had here. And I'm going to make it really long because the wing's over there and the tail's going to be way over here. Here's the center of gravity. So up here, remember, is the wing, its aerodynamic center, and we calculated the pitching moment about that center of gravity for the wing using all those dimensions, the h's and everything. We don't need that now because we're done with that. So draw this, draw the wing on one side of the page, draw the CG, and then put the tail down here, and the tail won't necessarily be along this zero lift wing. It could be wherever we want. It could be a high tail. It could be shifted down. So we're going to just put it down here. So here's the tail. And I've kind of exaggerated. That's probably too much. Make it like that. Notice I've tilted it down because we can do that. And that angle is called IT. Not for information technology, but it's the tail setting angle. It's just how much the tail is tilted down relative to the wing center line. Okay, so let's see, we've drawn the tail. And here's the aerodynamic center right here. So that's where the lift and the drag is going to act in the pure couple. And where's that thing located? We need moment arms. So let's call the distance back LT. So that's back to the aerodynamic center. And the vertical distance we're going to call ZT. And these are to the aerodynamic center here. How'd I get? That's not bad. So those are the moment arms we need. And now we need to draw the forces on the tail. They're lift and drag. And lift and drag are perpendicular and parallel to the relative wind, right? So where's the relative wind? We had V infinity coming up in like this to the wing. That's the angle of attack. So that same wind hits back here. But we know that there's downwash coming off the wing, right? There's flow over around the wingtips of the wing, goes like this, and so we actually get a reduction in the angle of attack at the tail. So we need to for that. Nothing magical, it happens. The flow comes around the wingtips, rolls around into these vortices, and it creates a downward flow at the tail. So we have to account for that. So the actual angle here of the relative wind is alpha reduced by epsilon. And then the angle of attack of the tail is the angle of to that flow. So it's going to be alpha minus epsilon and then reduced by I because this thing's tilted down, right? So the angle of attack of the tail is the angle of attack of the wing body reduced by the setting angle and epsilon. And that's how we're going to calculate the lift of the tail, is that's the angle of attack of it. All right, so the lift of the tail and the drag of the tail. My figure is a little bit off. This is perpendicular to V prime, and this is parallel to V prime. So that's the directions that those things act. So if I want to calculate the moment of LT, I have to account for the fact that it's tilted by this amount. right? So I'm going to have components. I need a vertical component and a horizontal component of that. And it's tilted relative to this line by this amount. That's the angle. So you're looking at this. We also have here a couple here. So we got a CM of the tail. So we're going to get another big complicated formula like we had for the wing. And then guess what? We're going to simplify it so that it's not so bad. In fact, we're going to simplify it enough that it's going to turn out that the moment of the tail is just going to be this force times this moment arm. Because we're going to say all these other angles are pretty small, and so that's pretty much tilted vertically and things like that. But I want to write out all the terms so that you can see them, because if it turns out this angle is not small, then so you have to include all that stuff. All right, just add some notes here. The lift of the tail is perpendicular to V prime, and the drag of the tail is parallel to V prime. V prime is V infinity tilted by that downwash angle epsilon. So all that stuff is happening at the tail. And so the tail moment is going to be the shear couple. I should have called this M. We haven't coefficientized it yet. I don't even know if that's a word, but I haven't turned it into a coefficient. So we're going to have the pure couple plus the two components of the lift drag. So it's just the geometry and the moment arms and all that junk. So we get the components of that times the Z's and the L's, and we get a big formula. So I'm going to write that up on the board, and then we're going to make it simple. So let me wait till everybody's caught up on that board, and then I'm going to shift over here. I'm assuming if you up here, then they're caught up. Is everybody good with this, or is anybody still writing? Okay. Yeah, shoot.
With the wing, the flow lines of the wing actually affect the flow number.
Yeah. That's what we're doing with that downwash.
Oh, okay.
Yeah. Technically, you could get this flow might be slightly slower than this because you have the wake. You can take that into account as well with Q infinity, but typically we don't. But the downwash angle does affect the flow. All right, let me shift the camera for those guys over. All right, so here's the sum of that stuff. Total moment of the tail is that pure couple. And here's the components of the lift and the drag. Times LT. So that's the vertical component. So that's cosine of LT. Cosine of the angle times LT. And then you get the vertical component of the drag, which is the sine. That's where we get those two terms. And then we got the horizontal component of the lift times ZT. And then the vertical, let's see, the horizontal component of the drag times ZT. So we have those two components. And you might say, well, why even write this out when we're just going to say, well, it's pretty much LT times LT, right? Again, that's only the case when the angle is small. And we have epsilon in here, so obviously if we subtract epsilon, we get even smaller. So if you end up working for a company and they're doing stall flight dynamics, you're going to say, well, you can't do that simplification, and you might impress your boss that you know that you can't because he knows it. But if you end up working for a fighter airplane company and they start doing high angle of attack maneuvers, like 45-degree angle of attack for some super maneuvers and stuff like that, then you have to include all these terms in there. When you do the homework, you're going to be doing the homework exactly the same as what we're doing here, except you're doing a canard airplane, so the wing is back here. The distances are all defined. You do it exactly the same. The wing formula is going to look exactly like what we did in class here today. The tail formula is going to look the same as what we did in class here today, except that its location is going to be up here. So pay attention to the signs of the different terms, because the lift here times that distance to the CG is going to be positive, whereas we had a negative here. But that's the only difference. So in fact, you can almost copy down what we've done in class to do the homework, except I want you to work through each term so you see where they come from. How are we doing on time? It just changed, 11:11. All right, so we're going to make all these approximations. We're going to say the drag is much, much less than the lift. The z distance is small compared to the horizontal distance. The cosine is pretty close to 1. The sine is pretty close to the angle, which is small. So we can pretty much say 0. So here we've got a small number and a small number multiplied times each other, so we can throw that out. Here we've got a small number times a small number, so we can throw that out. Here we've got small and small. And we're going to say the cosine is 1, so that's why we can say this is true. Now, you'll hear this in other classes as well, but when you're doing this kind of analysis and you say, well, this is small, the key is it's not just small, because how small is small, right? If you're talking about atoms, then we're talking really small. So what you really do is you say, okay, this is small compared to this term. This term is big compared to these, so we keep this one and we can neglect these. If we started plugging in numbers, you'd find out that we got like 1,000 here, and here we got maybe 10. And you'd say, well, yeah, that's small. We could neglect the 10 for an approximation, right? So what we're left with, when it's all done, is the moment of the tail. Oh, by the way, what happens to this? Is that small or not? Depends. Typically, the horizontal tail is symmetrical, which means this is small or 0. So in the book, he throws that away as well. He says you almost always make a horizontal tail out of foil because there's no cambered. Lots of approximations. But already you can see that when we start to, if we added this big formula to the big formula for the wing, we'd have all kinds of terms, right? And it would get complicated. And these are legitimate approximations that we can make. All right, so that's pretty easy. And you look at the figure and you could go, yeah, my force and there's my moment arm. So the last thing is we want to turn this into a coefficient. It's for the entire airplane. So we divide by Q infinity S C bar for the airplane. By the way, in 324, you almost always use Q infinity, right? Often, this is synonymous with what's called Q bar. They're both dynamic pressure. Q infinity is more related to V infinity for an airfoil, and when you start talking about Q bar, it's more of an average for the airplane as opposed to, but I'll use them interchangeably, and in the book they will as well. Let's check it. I got a text coming. I wanted to make sure that the class over there wasn't having problems. Okay, now here's a little wrinkle, and this is the last thing we'll do today because we're close to out of time. We've got this divided by Q infinity S C bar. I'm writing this up to remind us. The lift of the wing is the coefficient times Q infinity S. How do we calculate the lift of the tail from a lift coefficient? You'd look at it just off the top of your head, you'd say you multiply by Q infinity S, but S is the area of the wing. What does the area of the wing have to do with the lift of the tail? Absolutely nothing, right? In fact, if we were going to calculate the lift curve slope for this thing, for the tail, we'd use that big formula you guys just did in the quiz. And all of the information that goes into that is the airfoil data for the tail and the area of the tail and the aspect ratio of the tail based on its, or just for the tail as if it's its own flying wing. It's just a wing in a flow. And so by definition, we have to multiply this by the area of the wing to get the lift. Why did I write that? Tail, sorry. Totally messed up my whole argument there. Because the lift tail depends upon its own area, not the area of the wing. The wing is totally independent. And so we have to use in here when we turn this into a coefficient. It's real tempting to just say, well, this is CL of the tail. And that's not true. CL of the tail is based on its own area. So this is still CM of the tail in terms of the whole airplane. And whenever you have the tail in formula, we're going to always see this ST over S ratio. And the reason for that is just because of how you predict the lift of the tail. So this is CM of the tail is equal to minus CL of the tail. The Q infinities cancel out. Everybody follow that? So we put that in there. The Q infinities cancel out. If for some reason the wake of the whole wing reduces dynamic pressure at the tail, we'd have to include that ratio. But for this class, we'll just assume the dynamic pressure here is pretty much the same as here. And this whole combination of terms, people get tired of writing, and so they call that VH. And already, you're looking at this going, gosh, there's a lot of symbols and stuff and definitions and terms, right? What's VH? It's the ratio of the area of the tail times length to the area of the wing times C bar. It's something that's just related to the terminology and the anatomy of the airplane and the terms that we use. Like, I will expect you to know what H is. What is H? You'd think, where is H? Okay, H was at the picture of the wing, and it's the distance to what? Center of gravity in fractions of C bar, right? What's H in? That was the distance to the aerodynamic center of the wing. What's LT? Distance, center of gravity to the tail. It's just stuff you have to know. So if you ever watch TV shows or know somebody that went through medical school, they have to memorize the names of the bones and the muscles, and there's thousands of them, right, in the human body. So this is your job. You're essentially becoming doctors of airplanes, where you have to understand and know the names of the pieces and the parts of the airplane. Because we just call these, we have a common language, and you learn what the names are and the symbols are, and that's what they are. All right, let's see. We're done for today. See you guys on Monday. Check your email to find out whether we're have in person or it's totally Zoom. Everybody stay warm. Hopefully the heat in your apartment or wherever you're living is working. Yeah. About the what?
Area of the wing and the area of the tail. Why is it only, like, why does that not matter with the moment of the tail?
You're talking about here?
Yeah.
Yeah, by definition, we're talking about then when we're adding all of these pieces. We could change our definition here and say that's in terms of the area of the tail as well. So maybe the notation here is not so great. It's because this pitching moment is calculated based on the distance in the airplane as opposed to just, I don't know if that's a good explanation or not. Like if we were going to create a coefficient from that, just for the tail alone, we would define something called that. And that would be C bar of the tail. Yeah, but because what we're doing over here is for the whole airplane, we do it in terms of the wing area. Yeah.
Right, so the NC, the CMC for the whole thing itself.
Yeah.
Because the portion of it that's related to the.
Right. Right. As opposed to just talking about the tail all by itself. Yeah. Yeah. Right. I mean, we could say, well, let's normalize this with regard to respect to this room, right? It'd do work, but the area of the room has nothing to do with the lift, yeah. Yeah. Yeah, and that's what I was talking about. Sometimes you'll actually have to include the V prime squared if V prime is less. Okay. But typically we neglect that.
So typically we can just use V infinity squared.
Yeah,
for dynamic pressure.
yeah.
Okay.
It's an approximation, but it's usually pretty good.
Okay.
Yeah.